Welcome everybody to my introduction to quadrupeds. I think everyone who sees quadrupeds probably thinks of Boston Dynamics and Spot, and that's really no different for me. Ever since I saw Spot, I really just wanted to work with it, especially with the mentioned Python API and all that. But Spot is something like $70,000, if they even let you buy one to begin with. So how does somebody get into this field, and why? What excites me most about quadrupeds is the taking of your programming to the physical world. You can physically see it and interact with it, and there's just something really neat about doing that. I felt that before with small robot cars and quadcopters, but the options of what you can actually do with something like a robot car, they're pretty minimal, mostly because even the most benign surfaces or even transitions between surfaces can thwart a four-wheeled vehicle. Now, quadcopter drones are extremely versatile, but the battery life is 8 minutes or so. So that makes using it a pain, as well as just R&D a pain. Plus, drones also struggle with most payloads. With quadrupeds or robot dogs, you can navigate all kinds of different terrain, cross door transitions with no problems, go upstairs, walk on gravel, and so on. Functionally, quadrupeds can do incredible things. We know this to be true with dogs, cats, and so on. The quadrupeds that we have today are technically capable of running at very high speeds, climbing, and doing all sorts of really awesome maneuvers, but what currently holds them back most often is actually the software and the AI that drives them, because it's actually a fairly challenging AI problem just to walk around on four legs without falling, much less run or climb. So to me, this seems like a really interesting and cool problem to work on, but the question is, how do you even get started here? The barrier to entry is quite high if you want to buy your way in, and then I've also considered building my own, and this is definitely something that I would still like to do eventually, but building your own is really like a year or more of just R&D and trial and error, and I'd really like to have some idea of where I'm trying to go before I do that. And still, yet, my main interest is really in building the software and less about building the actual quadruped itself. While I was searching for options and trying to learn more about building from scratch, I did find a channel called MJ Bots where Josh here has been cataloging his multi-year long process in building his Quad A1. If you are interested in building from scratch and learning more about that, definitely check out his channel. I'll put a link in the description. But if nothing else, it should show you how much effort is required just to build the hardware and body of a quadruped. Another option is there are STLs and other build files for Spot Micro and even other quadrupeds on things like Thingiverse, which is a great starting point if you want to build one for yourself. I'll also link to that in the description if you're interested. But right at the perfect time, the Luwu team behind the XGO Mini project on Kickstarter reached out and asked if I would be interested in checking out their XGO Mini. So that was an obvious yes, and that's what I have here. I tend to shy away from promoting Kickstarters because especially from people I don't know, because you have no idea how that Kickstarter is going to pan out. So instead, I will just say here, this is purely my thoughts on the thing that I was sent. All the same risks are associated with Kickstarter campaigns. I don't know the company or the people behind this project. So I'm just happening to use this. And what I can say is the unit that I did receive is pretty awesome for what I am interested in doing. And again, I'll put a link to this campaign as well in the description. So right out of the box, there is a phone app that you can install and connect to the XGO Mini and control it over Bluetooth within 10 seconds. There's probably a bunch of small quadrupeds like this where you can just kind of control them, but really it's just kind of like a toy. So in the phone app, there are some demo actions and tricks that you can do. They're kind of silly, but should also spark some ideas of what you could program this bot to do. One thing, for example, is the range of motion of each of the legs is surprisingly large. It can basically scratch its own back. I also suspect I could make this thing climb up ledges, at least of a few inches, maybe not full human stairs, but still some significant climbing. I think they probably didn't include any climbing in the actions, because of the likelihood of failure and falling, but that's definitely one of the things I want to try. I think it's pretty clear that they tried to make this as stable as possible. The version I was sent also has an AI module on the front, which has a camera and then a computing and processing board on the front, so it does cool other demos like face tracking and gesture tracking and all that. So it's actually running deep learning models right there on that board, and again, that's pretty impressive to have included. And again, just kind of like sparks like ideas about things like maybe you could have like human detection and then you could actually follow the human around. So that's kind of interesting. So what excited me most about the XGO Mini, though, for my personal introduction to quads, is that the quadruped is completely programmable, and it actually has multiple layers of this programming. At the core of all these quadrupeds, you've got all your motors, and these motors have a controller. Even just to walk around, you need to address the movements of 3 motors per leg, along with the IMU, or the inertial measurement unit. And this makes, again, in my opinion, building and programming quadrupeds a pretty massive undertaking. So not only are you trying to develop the hardware and the design of all of the elements to be robust and functional, just doing a basic thing, like walking around without falling, is actually a fairly complex task. But with this quadruped, they have a serial protocol which kind of has everything you could possibly want, at least that's functionally capable on this quad. Essentially, there are some basic status things here, but then there are these 3 layers of control. So at the highest level layer, you have this whole body mode where really you're calling for very high level commands like move forward, backward, rotate along some specific axis, and so on. They also have all of the kind of demo tricks that the robot can do in this mode. So with whole body mode, you're using all of their algorithms for gait and just like moving around, rather than addressing each of the 12 motors individually. So imagine all you're trying to do is navigate a hallway or follow a human around or something like that. You would probably just need to use whole body mode, and you can still program the quadruped. But if that's not enough for you, you can get a bit deeper and do single leg mode. Here, you're controlling the entire leg by positioning the XYZ coordinates of just the feet. So again, rather than attempting to move the 3 motors individually just to move a leg in some custom way, you can just specify where you want that foot to be, and again, the algorithm can do it for you. And in this way, you could also specify, like if you need that foot to move to that position in a specific way, you could specify those XYZ coordinates in some specific order to get that to be the case. So here, you might want to use single leg mode if you're trying to get some custom action. So I think I could make this quadruped climb things like stairs, not full-size human stairs, but maybe 3-4 inches or so. And if I wanted to do that, this would probably be the mode that I would be programming the quadruped in to actually get the climbing action to take place. And then finally, maybe you want all the power. You have individual motor control as well. And the reason why you might want to do this is if you wanted to program the actual gait of the quadruped. So right now, the gait of this quadruped is likely meant as a very stable gait. My guess is this quadruped can actually run even faster. It just might not be as stable and may eventually trip and fall. And my guess is that's not something that they want to actually ship out. But you can probably improve this gait further. Also, the gait is most likely hand-coded by somebody on that team, whereas we could possibly use some sort of deep learning AI algorithm on the Raspberry Pi or maybe a more powerful board to control the gait. So again, if you're trying to get into that really, really deep control of the quadruped, this would be something you'd be interested in. To interface with the serial protocol, you have a ton of options, and that, along with the multi-tiered control at that serial level, is what makes this quadruped, at least for me, a great introduction. You could go through the AI module and or Bluetooth. The phone app that works out of the box, for example, is using Bluetooth, and I assume it actually is communicating with this protocol over Bluetooth. Unfortunately, I couldn't figure out how to interface with the AI module or the Bluetooth. Being an early review unit, I don't think they had the documentation fully ready. The XGO team was responsive to questions, but being on the other side of the world made communication take a while, and I'm not a patient man. My guess is if you could interact with this protocol over Bluetooth, it would be totally acceptable to do the whole body or even single leg control over Bluetooth, at least to some extent, unless you're trying to make the quad run or something like that, maybe. But then if you really wanted to do single motor control, my guess is if you're trying to do something like a gait algorithm, you really need that to be on, literally hardwired. But either way, getting something hardwired is really no big deal at all. You can just swap out the AI module for any other board that you want. I went with a Raspberry Pi just because the form fits the size, but anything that can transmit and receive serial should work just fine here. I ended up just strapping the Raspberry Pi to the top with an impact absorption separation device using an adjustable attachment mechanism. And now with this, the Raspberry Pi has Wi-Fi, so I can either communicate with it over Wi-Fi to issue live commands and control the quadruped that way, or I could save the instructions to the Raspberry Pi with a Pi file or any other file, and then I can run them at boot, or again, I can run them via SSH, or both. So again, algorithms that would be like controlling gate should probably be on the board. You could, start them up via SSH, but you probably want that all happening on the board. But if we want to have maybe a camera and some distance sensors, or even like LiDAR or something like that, the higher level AI stuff, just for navigation, we actually could communicate the sensor information over Wi-Fi or Bluetooth, and then use a more powerful machine to run more complex algorithms. So if you're trying to do a high-level task like walk around, you don't really have to do that on board. You could even communicate with like a cloud machine. So a ton of options there. So now let's see an example of serial communication with the XGO Mini. And in this case, I'm going to be using Python and PySerial, but you could use quite literally anything to communicate serially with this quadruped. So here I'm going to pull up the documentation again, and this is for that protocol. And again, if I had to ask for the protocol, they might actually share it when this actually gets shipped out. But if not, I'll put a link in the description so anybody can access this if you end up getting the same one. Here, just as a quick note, this is where you can... the AI module, I believe, was plugged in here, and essentially this is where my Pi goes. So I'm using the transmit, receive, and ground pin here, and then I'm actually using the 5-volt pin here to power my Raspberry Pi. And then here we've got the baud rate and everything else that you could need. So again, you just use this for the initial connection. And then finally we get to the communication format. So here we have the prefix, and this is all in like hex notation. And programming hex notation. So you have your prefix, and then you'll have a byte that is the length of the message. Then you'll have the actual message, and then your checksum, and then your suffix gets appended. So down here, we can see an example of, where is an example? I'll just try to find one. Yeah, okay, here we go. So this is your prefix. This is your, the length. This is read or write. This is a write. This is the actual message, this is your checksum, and then this is your suffix. So as you can see here, I've gone ahead and just written in prefix and suffix. So now back to the protocol documentation, we're going to scroll down to the address table here, and I think probably the first place that you're going to go is the whole unit control mode. And so everything's kind of separated by color here, so basically everything of these colors is the whole unit mode. So what we're going to, I think, start with, most obvious, would just be to make it go forward. So actually we'll end up building pretty much the same command that we saw above, but this is just kind of showing you kind of how to break that down into an actual program that you might write, so you're not handwriting these commands every single time. So for example, in this case, we know we can either read or write, so we can read what is the current, or we can write what we want it to actually be. And so to do that, we're going to find that address, and then at that address, what are we going to do? Well, we're going to try to write, this is the starting value, which I think is 128, should be like nothing, stand still. And then it ranges from everywhere from 0 to essentially 255 is what this FF notation is. So what we can do is just maybe make the robot go forward, stop, go back, stop, and that could be it. So we'll show that as an example. So coming back over to our code, we'll go ahead and come down and begin our function. So we'll start by defining a function. I'm going to call it whole x for whole body movement along the x-axis. So I am calling that the x-axis because that is what the documentation, how the documentation referred to it is. So x is forward and back, y is side to side, z is your up and down. So whole x, and then essentially we just want to pass to this speed. So the way that we'll go from here is to first we'll specify what is going to be the length of this, because essentially if you remember those command, like the order of command, it was prefix and then length. So in this case, it's just going to be 0x, what, 09. So it's just 9 bytes long. Then we're going to have read or write. And in this case, we are going to write. So that was the specified byte for writing. The next thing that we want is the actual command that we're going to pass. And in this case, again, going to the table, it was at 30 for the table for, where are you? Here. To address forward and backward movement. The default is 80 here. And what we want is to, or really it's 128. So 80 in hex notation, 128 naturally. So we're going to use 128 for like that default speed. And but as you can see, it's a range of this to this, which is essentially a range of 0 to 255. So what we're going to say is at the address of 30, what do we want to do? And in this case, we're going to pass whatever the speed was that we passed to the actual function itself. So again, this will be something like somewhere between 0 and 255, and 128 is middle, so like do nothing. 0 would be full backwards, 255 full speed ahead. So that's our command. Then we want to do the checksum, and again, referencing our documentation for checksum, it is the equivalent of, whoops, it's basically going to be 255 minus the sum of the length plus your message modulo 256. So thanks, Daniel, by the way. So I could not figure out how the heck I was supposed to write that. So the checksum in this case, boom, is 255 minus the sum of the length plus the row plus command. So in our case, the reader write and the command is part of the message, basically. So that's how this is, I suppose, but very difficult to read that. And then finally, we're going to just add this all together. So the actual data that we're going to send in is going to be the prefix plus the length plus the reader write plus the command plus the checksum plus the suffix. And then finally, we're actually ready to send that in. So the send information is going to be the bytes of data, and later you could just bytes up here, but whatever. And then finally, we're going to serial.write whatever we wanted to send. So, and the purpose of the checksum is just purely, it's a way for the receiving end to know, is this what you intended to actually send? Because again, one of the things that happens, like if the length is wrong, or if maybe something got timed out, or maybe something went wrong along the way, this is how you kind of know if something is awry. So we will go ahead and send that in, and that's basically all there is to it. So now we could just come down here and we could whole X, and we can go ahead and make it run forward. We will time dot sleep for 1 second, and then basically I'm just going to copy this, paste, paste, paste. So we'll do 128. So it'll run forward for a second. It'll stop for a second. It will go backwards for a full second. And then once again, it will stop for a second. So now what we can do is we can save that. And I've been using FileZilla to transfer. Yes. And now that is up on the machine, and pulling it over, we can execute that with Python 3. What did I call this? Xgo example.py. I'm just going to walk right off a box. 1 second. And now we can test it. And it worked. That's all for now. In the next video, I'll try to do something a little more advanced, so stay tuned for that. Thanks for watching, and I'll see you all in the next video.